Thanks, Ubne, for your uh, nice introduction. I'm really honored to be here. I really appreciate the number of people who have joined in this seminar. It's a sleepy hot afternoon, probably a good time for a nap, but instead everyone is here. So I really appreciate for you to join the seminar. So as Ume, you mentioned, I'm currently a faculty member at York University. And also one more thing that I didn't add to my bio because it just happened yesterday is that I started as the director of School of Information Technology, where we have more than 1,000 undergrad students as well as grad students. So it's a quite large department. So feeling really humbled and honored to serve the school as the director. So my talk today is about natural language interaction with data visualization. I understand and realize that many of you here are probably are not in the same research area. So rather than going into the nitty-gritty details and technical jargons, I would try to provide a gentle overview of the research. And if you feel like it's too complex, I guess feel free to ask me any questions for clarifications. Um, so I have quite a long slide deck, but I will try to wrap up on time. And near the 2020, things got very wrong because of the pandemic. So overall, regardless of the political party, everyone is quite negative about the economic situation in US. Now, what's interesting about this chart is that in addition to the chart, this report has also provided this textual explanation of this line chart that is kind of providing causal explanation. For example, it says just 22% American now rate economic condition as excellent or good, down sharply from 57%. So they're talking about this deep over here. So what we see from here is that language and vision, these are the two important modalities that we possess as a human being. And if we can combine these two modalities, then we can explain things in a more synergistic way, in a more effective way, rather than with only vision or only natural language. So that's why when I started my PhD, since then, in the last 10 years, I was one of the very few guys who were focusing on how to combine natural language and data visualization to help the user explore and understand large data sets. Now, in the last 10 years, I have been working on this idea of combining natural language processing and information visualization so that we can make data analytics more accessible to everyone. Um, Now, we can integrate natural language with visualization in two possible ways. One possible way is that we introduce natural language as input. So let's say um, we have some kind of natural language query or a question, and so then we visualize the result as an output. So in that case, natural language is um, acting as an input. Another way could be to use natural language as output, which is what we just show over here. In this case, we are showing a natural language as output, which can help people understand what's going on in the visualization. Now, with respect to these two goals, I have explored various projects that integrates natural language and data visualization both as input and output. So I have several papers that I've published in recent years on this topic, but For the sake of time, I'm going to only cover three papers in this presentation. So the first project I'm going to talk about is Char to text, where we use natural language as an output modality. The goal here is to automatically generate textual explanation to help people understand charts. The second type of project is where we integrate natural language as input. And the final one is question answering with charts and generating explanation. So these two projects are kind of focused on natural language as input, where we can use natural language to query with data visualization. So let's start with the first one, which is chart to text. So this is a project on which we have been working on for a couple of years, and we have published a couple of papers, one of which we just presented a month ago at the SCL conference. So if you don't know, SCL stands for Association for Computational Linguistics, which is the best conference in the area of natural language processing. And we just present this paper in that conference. So let me kind of introduce that paper. So this is the paper that we have worked in collaboration with another university, NTU at Singapore, and also with a company called Salesforce. And these are my students and collaborators from those two universities. So it's a quite heavy work with 7 people involved as collaborators. So in this paper, what we have tried is that we found out that while charts are being very helpful for communicating insights, there is no good automatic way of summarizing those charts. So for example, you have this bar chart that shows the value of goods in Singapore, but can we summarize this chart automatically? So you can see this is an example summary of this chart created by human, which said machinery and equipment was the highest or most valuable commodity, followed by something else. So it's kind of summarizing the key insights from this chart. So the problem here is quite simple. We have a chart as input, and we want to generate a textual caption or textual explanation as output. Now, if we can do that, that has a lot of applications. For example, you can imagine that if you automatically summarize a chart, then you can help the journalist or people who are writing reports by suggesting text for a given chart. Another example could be that readers who may not be familiar with complex data visualization, we can provide this summary to help them understand the critical insights in the chart. And then finally, but not the least, is that we can create accessible visualizations for those who are visually impaired or those who are fully blind. If we can generate the audio description, then they can at least understand the chart. This is particularly important because during the COVID, we have been exposed to a lot of charts talking about the number of cases, number of dates over time. But blind people, even though they need to understand this information, there is no good way they can do that. So I think that's quite an important application. Now, there are two key challenges if you want to address this problem of chart summarization or chart to text. The first one is that there is no significant data set or any sufficiently large data set that we can use for training the deep neural model. As we all know that deep learning models, often they require a lot of data to be able to properly train and be able to effectively perform the task. So the lack of large data set was a bottleneck in our case. Another problem is that there was no strong baseline neural models that we could use. So we wanted to develop several state-of-the-art neural models and apply them. So this is the kind of three main contributions of our paper. The first one is that we wanted to develop a new benchmark that consists of a huge amount of charts and their corresponding summary. The second one is that we wanted to develop a set of neural network models that can perform this task automatically. And then finally, we wanted to evaluate the the model in our new data. So in order to collect this data, we started with various possible sources online, including Statista and Q, which we have found to be quite suitable for this task. There are actually not many sources you will find both chart and corresponding summaries. So we find out that Statista was quite suitable in this case. So Statista is a website that provides information on economy, markets, opinion research, and they have over 34,000 charts that we have crawled. So we used a crawler that went to this Statista website and extracted all this information. The other source was the Pew. So Pew is a research institute which regularly publishes information about various social issues, demographic trends, and so on. One key difference between Statista and Pew dataset is that in case of Pew, there was no data table of the given chart, which means that somehow we will have to automatically understand the base of the chart, which is a kind of computer vision problem because the chart is an image form. So it was much more challenging than the Statista data. So from the Statista dataset, we scraped the links from the first 1,000 popular pages. And for each of the chart, we extracted all this metadata. But for Pew, the annotation process was not straightforward. That's because there was no explicit connection between the chart and the corresponding summary. So essentially what you have in Pew is an article consisting of multiple charts and many paragraphs. So it's not obvious which chart is talking about in which paragraph. So to solve this problem, what we did is in the first stage, we first extract the chart image, each chart image from the article. And then we identify what could be the most relevant paragraphs. So we take the 5 paragraphs that are above the chart image and 5 paragraphs that are below the chart image. And then from there, we apply an annotation criteria using Mechanical Turk. So if you don't know Mechanical Turk, it's basically an online platform in Amazon where basically you can hire people to work on various micro tasks like small tasks. So in this case, we asked the Mechanical Turkers to select the relevant paragraph. So given a paragraph, they would say whether this paragraph is relevant to the chart or not. So in this way, we ended up finding what are the relevant paragraphs. Of course, sometimes there could be disagreements between the two annotators for a given paragraph. So in that case, we have manually analyzed those disagreements and resolved by ourselves. So now that we have done this annotation, the next step was to analyze these two datasets and see how they look like. So what we have found is that they have a diverse range of charts. Most frequent charts are bars and line charts. They also have some pies and other stuff. The topics were quite broad, ranging from politics, society, health, and economy. And summary tend to be quite longer in case of Pew because they tend to have more reasoning aspect and contextual information. So summaries tend to be longer in that data. Now, once we have crawled these two data sets and annotate them, we define two possible task settings. in the first setting, we assume that in addition to the chart, the data table of this chart is given. In the second problem setup, we assume that no, the data table is actually not available. We only have the chart in image format. Therefore, this setup is more complex. So the idea here is that you have the chart as input and you have to generate a summary that looks like this gold sum. Now let's talk about how we have developed the model. So we have tried out several models. We started with image captioning models that are the state-of-the-art models for regular image captioning. Then we have also tried out the chart-to-text model, which is a transformer-based model, a neural network-based model that we have developed before. And we have tried out another two models which are based on BART and T5. Basically, BART and T5 are again transformer-based models which are trained, pre-trained on a huge amount of corpora. So we found them to be quite effective in other tasks for generation, like text generated tasks, so we use them. This is kind of an example of how the chart-to-text model works. So again, this is a paper that I have published with another student. And in this model, basically, you provide the data table of the chart like this, and then you have an encoder which predicts that which table cells are important, which are then sent to the transformer decoder, and then you pass through the softmax layer, which gives you the generated summary. So I probably went too quickly, but on a high level, the idea here is that you have an encoder that predicts what information is important within the data table, and then you have the decoder which generates the caption based on this predicted information. I'm going to skip this one. And then finally, the BART or T5 model, again, they're encoder-decoder based model. You write the data table as input and you separate the tokens. So you provide the title of the chart, and then also you provide the data table, and then it generates the target sum. So one question here is that we have two different problem setups. In one case, we assume that the chart and the data table is available, whereas in the second setup, we assume that only the chart image is available, right? So when only the chart is available, we use the optical character return, the state-of-the-art model, and then we simply use the output of that OCR model, the textual tokens of the image, as the input to the this BART or T5 model. So in basically when we have the data table available, then we provide the data table as input. And if we don't have the data table, then we provide the tokens from the image chart as input. Okay, so I guess we provide a very quick overview of the models. Now let's talk about how it looks like, how the results look. These are some of the automatic metrics that try to measure some of the performance. For example, Blue and BlueRT are commonly used for various language translation tasks and also summarization tasks. Another score is slider, and which gives you a sense of how fluent is the text generation. And then content selection basically measures how many of the table cells that were mentioned in the gold summary, and they're also mentioned in the generated. So what we can see here is that winner here is mostly the BART and the T5 models. So these are the two state-of-the-art models for natural language generation. So it's not quite surprising that they were doing pretty well. We also have some variations of models. For example, in some variation, we have used the tab prefix. So the tabs are the ones where we have access to the data table. Therefore, it's not surprising that the results were much better when you have access to the data table. So for example, this one is the best public model. Whereas when you have the OCR, when you don't have access to the data table, performance could fall, especially on the part. On the Pew data set, we did not have access to the underlying data table. Therefore, we don't have any tab model or tabular. So instead of OCR models, and we noticed that image captioning models perform very probably because they were originally designed for image tasks where you have objects and natural scenes. But here we have charts with natural scenes, so the performance was quite worse over there. Again, T5 was the winner here, where we used the OCR as human evolution also confirmed this. For example, when we compare between models, we found out that on the factual correctness, when you have access to the data table, factual correctness dramatically over the OCR, simply because when you use the OCR, you have lots of errors in the extraction of the text, whereas the tab, basically you have access to the underlying data table, therefore it was much more factually correct. When you compare between the gold summary, obviously gold summary is better, but in some cases we see that they actually were doing quite well on certain aspects. For example, in case of fluency, there are lots of ties, which means that the summaries generated by the models are quite fluent. Just wanted to show you some example generated outputs and what kind of errors that we were facing. So we manually analyzed the generated outputs. Here you can see an output from OCR T5 model. So you see that as of December 2020, Cristiano Ronaldo was the Instagram account with the most followers worldwide. So we see that there is a bit flip between the values because Cristiano Ronaldo actually have 243.95 Instagram followers as opposed to 380, but the model kind of misjudged between these two because the model does not have access to the underlying data table. Another example here says Brazilian singer had 2.3 million followers. So the you can see that 243 is actually not belonging to the Brazilian singer. It's belonging to the Cristiano Ronaldo. This is kind of error that can be characterized as hallucinations. So what happened is that model, when it tries to learn from the training data, often it uses model token that it sees during the output token during testing that were learned during the training. So that's the hallucination problem. So irrelevant tokens that are outputted due to the training examples is kind of a problem. Another problem is computer vision challenge. Sometimes it cannot extract data values correctly. So that's something that we need to improve in the future. But I will stress here is that while this example shows some errors, we also saw many examples that are quite impressive in terms of generating good summaries from the chart. So we really feel that there are lots of opportunities and applications of this task of chart building. Okay, do you have any quick questions before we move on? Okay, if
Assalamu
not,
alaikum.
walaikum assalam.
This is Abdullah Mamun.
Yes, please go ahead.
Yeah, so as one of the prime limitation is the data set. So
Mhm.
is there any particular format of charts that we have to check on the model? Like, is it available for the pie chart or other formats?
Yeah, that's a good question. I think one of the main bottlenecks that we had is there are lots of charts that you can create using those automatic chart construction tools like PyTorch, Matplotlib, or whatever tools. The problem is that we don't have human written summaries uh, for those charts. So one possible way could be to ask people to write summaries or captions for charts. Um, but that is costly because you can only collect maybe a few hundred or thousand summaries in that way because you'll have to find good write good in writing and have and are proficient in English and so on. So that we had to crawl whatever we can find it for free. So like extracting captions from Statista and View was cheaper for us, but I think it's a problem for us to to build a large data set. Still, the data set is not large enough, I would say.
Okay, Dr. Enamul, may
Yeah,
I supplementary question just from
sure.
the collaborative research point of view? I think you have a good amount of data set actually. Yeah, so is it shareable actually in some cases is this data set is shareable actually as a data set is it I think is it
Yeah.
open access your data set
Yeah,
is
yeah. So yeah,
is it
the policy of our research lab is that we make everything publicly available. So the source code as well as the data set is already publicly available. I can like quickly share with you right after the meeting, or you can just search for ACL. Yeah,
thank
yeah,
you very much.
yeah. So we have a GitHub repository that contains both the dataset and the source code of the models. Okay, so now let's move on to our next topic, which is
Sorry, this is
yeah, go
Mamun
ahead.
again. So may I have the follow-up question?
Yeah, yeah, sure.
As we are talking about the data set and about the benchmark, so now
Hmm.
how we will validate our task, mean that how we claim that, okay, our work is gonna be perfect or approximate to that. So how we are validating our results?
Um, I guess if I understand your questions correctly, I think so. When we propose this benchmark, we have proposed several things. So first of all, we provide the data set. Second, we provide the source code of all the models. And then finally, we provide the metric information. So these are the different benchmark metrics. So if you want to develop a new model for this problem and want to say that, okay, your model is probably better in certain ways on certain measures, then you can just run the experiment on this data set with your new model and then see how the results looks like. So always that could be a nice direction to try out new model. Yeah, I see one more hand, and then we can move on to the next part.
Thank you for my side.
Yeah. Okay. Is there any more hand? I
We
saw
are
your
not
hand.
facing the query actually in the chat box. That
Mhm.
is BART, B-A-R-T and B-E-R-T. Is there
Yeah.
any, these two are transfer learning model, we know that means
Yeah.
transformer based model. So what is there, can you, what is the difference between these two?
Yeah. I
Again,
mean,
chat box.
yeah, both of them are a transformer-based model. I think the BERT is the one that came first. The BERT is basically the idea that you have. you are generating vector representation for words.
Yes, yes.
So previously, the most popular one was word2vec. Word2vec was quite popular for generating vector representation of words. But word2vector has the major limitation. It could not generate the vector in the context of the sentence, the other words. So if I say, I want to book a flight, then you have a vector. And then if I say, I am reading a book, then the book is being used in a different context, right? But in case of word2vec, it will consider the both words to have the same vector representation. So this was a major limitation for word2vec because it's going to always give you the same vector regardless of how it's being used in different sentences. But BERT, it's a transformer-based model that can generate word vectors in terms of context. So it considers the other words in the same sentence, the contextual embeddings. So that is BERT. The other one, BART, is another transformer-based model. I think it's just a slightly upgraded version on top of transformer, but I do not recall the nitty-gritty details of that. But I think in terms of performance, practically speaking, they work quite closely. Like there is not big difference in terms of performance between BERT and BART.
Thank you, Dr. Enamul.
Okay, so I guess I'm gonna move to the next project as the time is getting short. So the next project I want to quickly talk about is question answering with Char. So the idea of question answering is that so this is the work again we have worked with several other people in this ACL just a month ago. So the idea here is that you have a chart as input, and the goal here is to answer a question about that chart. So let's say, what's the peak value of the orange line, right? So you see this line chart, which has this orange line, and you notice that the peak value over here is 87. And then another question is, which year has the most divergent opinion about Brazil's economy? So you see that these people are thinking economy is good, and these people are thinking the economy is bad. And the most divergence opinion was in 2015. So that's the correct answer. So can we automatically answer these kind of questions about chart? If we can do that, that can be very helpful in various applications because it can reduce the cognitive burden when we try to analyze charts. We can just simply write down the question or just use our microphone to ask the question and it can give me the answer immediately, right? Now, one challenge is that often this question has lots of mathematical reasoning aspect as well as visual reasoning aspect. For example, over here, you have this peak, orange line. These are the words that are specific to chart and not specific to other things. Similarly, there are lots of mathematical expressions that needs to be used here. For example, to answer this question, you need to find out the difference between the two lines at each year and then figure out when it was maximum. So you have some mathematical operation. Now, this kind of questions that involves lots of mathematical and visual reasoning were not really addressed in some of the previous question answering data set. So again, in this problem, we were exploring how to develop a benchmark data set first that contains this kind of question. So if you noticed in the early data sets, there were a bunch of different problems. One problem was that they were generating the charts synthetically using some programming tools, and they are just using random words. For example, you see this word here in this bar chart are reason, month, and silver. So semantically speaking, there is no meaning at all. Like what's the similarity or relatedness between reason or month and silver? So they're basically just using some random words and they're just creating bar charts automatically out of those random words. Another issue is that the data set itself is not real. So they were using random data generator to generate these charts. So to address this problem, the first thing that we on is how can we collect a lot more real world charts and then create human authored question answers. And then of course we develop several state-of-the-art models and evaluate our approach. So in order to find charts, we explored various online sources and then ended up with 4 different sources. The first 2 I already introduced in the previous project, Statista and Pew. And then in addition, we had OECD and OWD, which are some data set about global economy and finance and other things. So these are some sample charts, and we then create some human authored through crowdsourcing. So the idea here is that we give a chart and then for which the answers cannot be extracted from the chart itself. For example, it could refer to some information that is outside of the chart. So we had to manually go through these question answer pairs to figure out those. Okay, so just to summarize the data set, we find out that there were about 10,000 human authored question and then another 23,000 machine generated questions through this process. So there are 4 main types of questions. Data retrieval is the simple one. The visual ones refer to some of the visual properties in the chart. For example, rightmost, blue, bar, these are some chart specific terms. Compositional questions are the ones that involve multiple mathematical operations. So these are arguably more challenging. And we noticed that our data set mostly have this kind of challenging questions as opposed to data retrieval questions. So this suggests that our data set is quite challenging actually to solve the problem. So this is how our question answering pipeline looks like. So this is the automatic pipeline, which takes a chart as input. And then it also takes the question. From the chart itself, it first extracts the data and then generate the data table. And then it also uses the image feature from the convolutional neural network and then send both the data table and the image feature to the model, which then generates the answer. So that's kind of the overview of our model. Now, for the data extraction, there are 2 setups here. In one case, we assume that the data table is given. So then the problem is simpler. Alternatively, in another case, we assume that the extracted data table is not given. So we'll have to extract it manually. So the way we extract the data table out of the chart is very briefly, we first detect the chart elements using a model called key point detection network. And then second, we use a OCR model called Craft, which is one of the state-of-the-art model for OCR. So as you can see, we first element all the elements here. So they're highlighted in different colors. And then next, we extract the OCR tokens. So for example, from here, we kind of estimate that the value of this bar is 20.1. The value of this is 30 and so on. So what we do in this case simply is, let's say, if you have this y-axis, you can see how many pixels each of these axis level is taking from bottom. And then based on that, you can estimate how much this bar height is. And then from there, you can kind of interpolate or kind of get the idea how much the value of this bar will be. So based on that, we recover the fully structured histogram snapshot. And then these are the years, these are the values. Of course, this is not completely correct all the time. So there are errors that can happen during this data extraction. Now let's talk about the model itself. So we have used 2 main models. One is called Tapas, which was originally developed for table question answering, where the idea is that you have taken a data table and a question as input, and then you try to answer the question. But in this case, it does not consider any visual features of the chart because the input is just a table. So to address the problem, we extend the original tapas model by considering the visual features in addition. So this is how our model works. So you have the question and the data table as input. And then additionally, we extract the chart image patches using CNN, convolutional neural network. And then we have this cross-modality encoder that kind of provide cross-attention between both visual features and the textual features. And then at the end, the goal is to predict what operation should we apply. So sum, average, count, difference ratio. These are the different possible operations that we can apply. So we simply predict which cells we should select, and then we apply the predicted operation on those tables. We also use the T5 model, which consider the task to be a generation task. So instead of predicting the operation in the cell, the model figures out by itself internally. So it just generates the answer without predicting the operation or cells explicitly. So it automatically figure all those things. Now, what we have found is that this is quite a giant table. So just to give you a quick overview of the table, we have various data sets like figure QA, DB plot QA, which was early data set. And then we have our own new data set, which is the chart QA. And then we noticed that the tapas model was quite good on existing data sets. And then we noticed that when the gold data table is not provided, then pre-fill model was doing slightly better on the figure QA, but vision tapas was better on the other data. But more importantly, we noticed that on the chart QA dataset, the vision tapas was doing better. So this is suggesting that when we combine the visual features and the table features, then we can really address those questions very well. Another thing we noticed is that still the accuracy is quite low on the chart QA dataset, which means that the dataset is quite challenging and still there is a lot of room to improve accuracy. So I would encourage you, if you're interested in this topic, to again take advantage of the dataset and code and try out new models. Okay, in terms of errors, we found out that the model tends to have difficulties in terms of handling nested operations. So let's say if you have some operations and then you apply another operation on top of that. So if you have nested operations, then the model has some issues addressing that. We also found out that often it cannot extract the data accurately from the chart. So there are some computer vision challenges over there. Okay, so this was a quick overview of the chart QA project. I guess my time is out, so I will try to wrap in a couple of minutes. But let me quickly show you a quick overview. Yeah.
You need to be very much hurry because we are going through question and answering. So you will have some more time. Okay, I think it will not be. Is it even concluding remarks? You are almost at the end of the presentation, I think.
Yeah. So I will try to wrap up in a couple of minutes. So So the last project, which is also about question answering, this was done in collaboration with Stanford University while I was a postdoc at Stanford and later on as a faculty member. So over here, what we have found out is that still, if you notice, the accuracy is not very good. The accuracy is hovering around 50%. So how do we actually use it for practical application when the accuracy is not very good? So one thing we found out is that if we can explain to the end user how the model has computed the answer to the question, that can help helpful to the user a lot, because it can improve the explainability of the model. As we all know that explainability is a big challenge for artificial intelligence models, and so over here we wanted to improve the explainability of the models. So in particular, we wanted to improve the transparency and the trust of the model by explaining how the model computes the answer. So let me show you, I'm going to skip this part. Let me show you how we generate this explanation. So let's say you have this question, which religion has the shortest orange component? And then you have this chart, and this is the data table. So then we what we do is that we first convert the visual reference to the chart into the corresponding word. For example, shortest orange component is actually referring to this word common because it's orange. So we convert the orange into common. And then next we send it to the SEMPRE, which is again a question answering model with table. So we provide this data table and the question as input. Now, while generating the answer, the model generates this lambda expression, which is basically a logical form. So you can imagine it's kind of like an equation. So you have, if you want to answer this question, then you will have to take the least common percentage. So you have to take the arc mean of religion. So this is basically a kind of logical expression that we need to evaluate in order to answer this question. So the way we generate the explanation is by transforming this logical expression into a corresponding simple textual explanation. So in this case, it's going to say, I looked up religion with the least percentage of common. So this is how I compute the answer to this question. So the corresponding visual explanation would refer to some visual properties of the chart. So the question was, which religion has the least common percentage? And then the explanation says, oh, the way I compute the answer is by looking up religion for the shortest orange bar. So I simply find out which one is the shortest orange bar, and that's the answer. So now we can confidently understand that, yeah, the model has computed the answer correctly because the explanation is exactly what we expected, right? We expected that to answer this question, it would find out the bar with the shortest orange component, and this is exactly, this has been done. So these are some of the explanations. For example, what's the difference between Gallup and Quinnipiac? In this case, the answer is correct. If you see the Gallup and Quinnipiac are, I think, some pollsters over there. So it simply says I compute the difference between Quinnipiac and Gallup, which is pointed. Another example is what position is LPOS in. So in this case, the answer is incorrect because the position of LPOS is 1 to 3, so over here. So we know that the answer is incorrect because it says I looked up the length of the bar. So instead of measuring the position, it computes the length of the bar, which is incorrect. So this is quite helpful, as you can see from this example, that explaining how the model computes the answer is quite useful. And we wanted to further verify this through a user study. And so in the user study, we have provided with 4 different conditions. In one case, we provide no explanation at all. In another case, we provide the human written explanation of the answer. And then another 2 cases, we provide the visual and non-visual version of the automatic explanation. So we run a user study with 16 participants with 20 chart question answer explanation. And then we evaluate the transparency, trust, and use. So very quickly, we found out that if we provide the explanation to the user, that can significantly improve the transparency. So notice that if you provide no explanation at all, then people don't find the model to be transparent. Whereas if we provide visual explanation, then they're much better. So we found out that visual explanation is even more effective than human explanation, because in human explanation, people often use different word variations, so it's not always consistent. Whereas in case of visual explanation, it provides visual reference and it's always provide a consistent template of the explanation. So that was quite helpful. Again, in terms of trust, we found out that visual explanation was quite similar to human explanation, whereas no explanation was not very helpful. So overall, the takeaway from here is that if we explain how the model answers the question, then it improves the transparency and the trustworthiness of it. All right, so we provided all these different projects. One was about automatic chart captioning, another was chart question answering. For the sake of time, I'm not going to cover any other project. And just to wrap up, what we learned from here is that if we can complement data visualization with natural language, that can be very helpful for comprehension. Also, we learned that if we can explain the model's output, that can enhance the transparency and trust. And then finally, the solutions that we develop needs to be generalizable so that it works across various charts. All right, so with all that, um, I'm, uh, I'm going to thank all my co-authors and people who have contributed to all these projects that I discussed today. And another thing is that we actively seek good students for doing PhD and MSc. So feel free to ping me if you have a strong background and interest in this topic. So with that, I would like to end my talk here, and thanks for your attention. Happy to take any questions.
Thank you so much, sir, for such a versatile session on natural language interaction and integrating it in data science and analytics. I'm quite optimistic that your lecture has given the participants to get some insights into the world of data visualization and handling large data sets. Now, the most interactive session that we all are waiting for, the questionnaire session. I'd like to invite all the participants to ask relevant questions to our keynote speaker, Dr. Prince. And I'd like to request them as well to make their questions short and precise so that we can end it within 4:30 p.m. because this is the timeline of our questionnaire session. I'd like to request Professor Prince to take the questions accordingly. Thank you, sir.
Any questions? Feel free to